start in with a reasonably close. Good. I think we're all set there.
Good.
Just to make it safe, I'll put the lights a little bit closer. A little bit more.
Yep.
It doesn't bother you.
It's pull these down.
Trouble with leads.
Yeah, too many wires around, aren't there?
Very good.
I was wondering if you were going to sit on the table.
I'll sit on sit over on the couch side. All right. Very good. Okay.
You can have the chair and I can move it.
Is this one functioning now?
Let's test it.
I think it must be so loose in here. No?
Yeah, it's fine.
All right.
Very good. Okay. Well, fine, John. Well, of course, as I mentioned over the phone, I would like to just have an informal conversation with you on some of the principles of radio exposure and the health effects and the lack of health effects and so forth. And so I think we can just go at this very informally and see how and cover ground. I think in about an hour and a quarter or something like that. Should give me a good record of some of your ideas and findings throughout this. So, are you ready to go? You do your regular focus in close, and then give a manual focus. Is it actually right manual focus? So it's right in focus now. Good. So every time you zoom, it'll still remain in focus. Good. All right. Well, we're all set then. Well, very good. Well, let's see. So I'll start right in, John, and I'll with something like the date today and your name, and then I'll start asking a few questions, and we'll just have a normal conversation on it. All right. Today is February 1st, 1989, and I'm privileged to have Dr. John Totter to interview today on the subject of radiation effects. And so, John, would you please start out by describing how you got into this particular field of study, starting with some of your background in academic work?
Oh, thank you. Yes, I had majored in chemistry at the University of Wyoming and got interested there in biochemistry and went to Iowa on a graduate assistantship and worked for C.P. Berg and to finish my PhD graduate work, which was done in the field of amino acid metabolism. And I finished there in 1938, taught for a year at West Virginia, and then for a number of years at the University of Arkansas Medical School at Little Rock. And there was much interested in the development of folic acid and studying its chemistry and biochemistry.
At that time, was folic acid being investigated as a possible therapeutic agent?
As a possible therapeutic agent, but at that time we had no dream of a connection with radiation. But when Ray Edwards came to visit our school, Ray was a member of the staff at the Manhattan Project in the chemistry division. I think he worked for Coriell.
Oh, yes.
And he was the one who started talking to us about radiation and so forth. And it did occur to us that since the earliest human signs of radiation exposure were lowered white cell count, and it's exactly what we were working with because folic acid is required for white cell production. And so we began to think of it as a possible therapeutic agent for radiation sickness of various kinds.
Oh, yes.
And we actually did quite a bit of work on that. And I came to Oak Ridge then as a participant for 6 months and worked with C. Carter in the biology division and did study the effects of folic acid deficiency on the production of the purines and pyrimidines, which are required in the nucleus of white cells. And the absence of folic acid gives a syndrome in animals that are susceptible to this, similar to whole body radiation. And so this was what connected me with the work here, and I thought I might be able to contribute something by putting these things together.
Yes. But folic acid, did it ever reach the stage where it was used as a possible therapeutic agent in medicine for a stimulation of white blood cells, or were there other agents which turned out to be better?
Well, it has been used a lot for it, and of course for nutritional anemia, it's essential. You have to use it for that. But this picture got a little confused because it seemed to help pernicious anemia patients, although their deficiency is deficiency of vitamin B12 and not of folic acid. But it did stimulate production of cells in the pernicious anemia patient, but didn't cure the other defects of pernicious anemia. So nowadays one is quite clear about where one should use one and one the other, where the other. In anemias of pregnancy, then folic acid is the drug of choice, and in anemias such as pernicious anemia, use B12. But both things are necessary.
Oh, yeah. See, I have heard of some complications of folic acid used in pregnancy anemia and so forth. Have you ever heard of that?
No, I had not been aware of that. I haven't followed the field recently.
Yeah. But, of course, with every drug, there's a certain small percentage of perhaps odd reactions that you will get in various Well, fine. Well, that's not too vital, but going from there, how did you branch out then from your interest?
Well, I came to a couple of years after I'd been a participant. I came back to Oak Ridge and joined the biology division and started then working on attempting to follow the biochemistry of changes following irradiation into as early a stage after irradiation as possible to do. And of course, you know that Waldo Cohn and Charles Carter were working on separations methods for the purines and pyrimidines, which are the things that are seem to be affected most by radiation. And the methods available then just weren't good enough to track down to, say, a few minutes. You could see if you irradiated, for example, hen egg, when the embryo was 5 days or so old, you could see changes following 5,000 rads of exposure, but you couldn't measure them. You couldn't measure them objectively, but you could see the actual changes in the embryo. So following of that, just had to wait a long time for development of sufficiently good methods to understand what was going on.
Yes, I noticed you started using some of the units of exposure, and you mentioned 5,000 rads, and so much of our literature and discussion today, we speak of 5, 10 millirads and so forth. And so sometimes there gets to be quite a bit of confusion because you're off by orders of magnitude, and there's a slippage there in the discussions.
Well, you put your finger on what has really been the difficulty of understanding radiation, because our methods required very heavy doses at that time, in the near lethal doses, which for a chicken or for a rat would be around 500-600 rads, which is 5 or 6 grays by modern usage, and 500 rads would be 500,000 millirads. So
yeah.
our methods were simply not fine enough to pick up the changes with millirads or a few rads.
Oh, yeah.
And they only have recently begun to get that way, and that probably accounts for much of the confusion and difficulty that people have for having a proper feel for the magnitude of these doses.
Yes, and let's see, before we get further, there's as I say, there's a matter of you go from mads to millirads, and you're talking about these, and then also to add to confusion, there will be some new units brought in, such as sieverts and millisieverts and so forth. And, is there any simple way to get these connected together?
Well,
a common translation unit.
There are ways, of course, but nothing is very simple about them. The Gray and the sievert are similar. The Gray, named after L.H. Gray, is a British scientist who was active in radiobiology, is a flux measure or an exposure measure. The sievert is similar to it, but it's the absorbed dose from the exposure to a certain number of grays. 1 gray is an absorbed dose is 1 sievert. And these are about 100 rads or 100 rems for the old, to connect the old ones. But they are all connected mathematically back to the energy units that the physicists use.
Oh, yeah.
So they're consistent with all of the units now used in physics, if we use the modern unit.
Yeah.
But the old original unit was the Roentgen, and it was close to what we call a rad now. And the absorbed doses are rem would be equivalent to exposure of a rad, and we called the ratio between the exposure and the absorbed dose is called the biological effectiveness.
Oh, yeah.
Relative biological effectiveness. And these were good terms, but they're dropping out of usage now quite a bit because they're going to the modern nomenclature. But I don't know how to make this simple for the ordinary listener.
Yes, of course, whenever we get into discussions in the media or even in Congress, these things apparently become very hopelessly entangled, and there's a lot of misunderstanding, I think, is generated when you go from grays to sieverts to rem to rad and millirad and so forth.
And it's unfortunate, but it's confusing for scientists as well as for lay people.
All right. Well, fine. Well, I think that clarifies that part of this. Well, let's go on then to your further extension of your research work as you follow through.
Well, when I came here to Oak Ridge in 1950, Dr. Hollander was chief of the biology division, and he was pushing an interest in 2 things. One was called the oxygen effect, and this was discovered by L.H. Gray, which is very simply that when you expose something biological, a live animal or tissue, to radiation, in the absence of oxygen, you get less effect than in the presence of oxygen. And the difference is about 2 or 2.5 fold. That is, and this began to be considered a direct and an indirect effect. The direct effect was supposed to be the actual collision of a particle or a gamma ray with an atom to expel an electron. The indirect effect comes about because the electron is in tissue is absorbed by water, and water splits into a radical and an ion when it accepts a stray electron. And it's the radicals that we're interested in because they're the damaging things to tissue. And they can disrupt the nucleic acid in the tissue and give rise to mutations or all sorts of other trouble. And about, as I say, 60% of the effect seems to be this indirect effect of the electrons knocked loose by the absorption of the energetic ray.
Now, with regard to specifically the effects you measure by the effects by counting mutations is one
That's
thing.
one way.
Yes. There are other things, I suppose, such as life shortening, or what are some of the other manifestations, or are there histological things that you can observe quantitatively? In other words, what are some of the quantitative ways in which you can assess the effect of
on biological material? Well, the counting of the mutations is an indirect way of measuring it. A more direct way is to extract the nucleic acid and count the breaks. And find out how many strands of the long nucleic acid assemblies are broken by the radiation, because if one of the purines or pyrimidines or sugars on the strand accept an electron, it makes it energetic enough to break. And then we lose viscosity if we're measuring. That's one measure of it, is to measure the thickness. The longer the strands are, the more jelly-like the solution is that has the nucleic acid in it. And so we can measure the rigidity or fluidity of the gel and get some notion of the chemical damage done. We can follow those things in a variety of ways, but the way that was in common use at that time, the most effective way, was simply to measure survival of some small organism like a bacterium. Expose it to radiation and measure how many colony-forming units are left out of a given number exposed. And that led, of course, the physical people understood a lot more about radiation than the biologists did. Biology was biological objects were pretty crude things to work with. And radiation. And the target theory arose out of that. This I think, had a great effect on what people later believed about the effects of radiation. The targeting business was very analogous to Dr. Rutherford's and his colleagues' means of measuring the volume of the nucleus of atoms. Shoot at a target, you don't know how big it is, but if you know how many shots you put into an area or volume, you can tell by the survival of the target itself, which in this case will be a bacterium or a virus, let's say. You can, by shooting enough bullets into the volume where you know it is, you can tell how frequently you will hit it, and then calculate its actual volume from the frequency of hits.
Oh, yes.
So this worked very well for small viruses. You could determine the size of the virus by how sensitive it was to radiation. And radiation being the gun you shoot the bullets with.
Oh, yes. Very, very neat technique there.
That idea dominated, that there is a target that you had to hit to get some effect. And that still dominates the connection, the thought about connection between cancer and radiation. People have used it to try to figure how many steps a cell goes through before it becomes a cancer. It so happens that the frequency of cancer, measured against the age of an individual, goes up as the 6th or 7th power of the age.
Oh, yes.
And that has been interpreted by some people as the single cell which eventually becomes a cancer requires 6 or 7 hits. Of course, it may be the progeny of the cell.
Oh, yes.
Not the cell itself.
Mm-hmm.
But I think this has misled people very seriously about the connection between cancer and radiation. Because if one takes a disease like cardiovascular disease and follows its occurrence with age, it'll go through the same, about the same relationship to age, about the 6th or 7th power of the age. The frequency of cardiovascular disease in a population goes as about the 6th or 7th power of the age. Doubles every 5 or 6 or 7 years in frequency. So, and there's nothing you could think of about cardiovascular disease that would lead you to believe that there's a target in the cell that you have to hit to get cardiovascular disease.
Oh, yeah.
You think of this about cancer because you think a mutation is what causes cancer.
Oh, yeah.
But if you had not this preconception, you might not think of that as a target at all.
Yeah.
And I believe this has misled people an awful lot about cancer.
Now, with regard to the mechanism, of course, the way radiation manifests itself in the bodies of animals or humans, one of them is shortening of life, one of them cancer production, and particularly a subset leukemia production is one. And let's see, are there any other manifestations that we look at?
There
of course, the mutations.
There are early manifestations of whole body radiation. You have to distinguish between partial body and whole body radiation because they behave differently.
Oh, yeah. Mm-hmm.
And that's a point that I would like to get to. You're correct. You named several of the methods. In the early days, in the 50s and 60s, there was still pretty strong belief. I think this was originated by Paul Henshaw, who was a pioneer in radiation work and was here during the war at Oak Ridge, that there was life shortening, what they call non-specific life shortening, that is a life shortening owing to all causes of death that are connected with old age. But so much work has been done with high cancer strains of mice that they now believe that at least in those, all of the life shortening is due to increase in the rate of cancer and the age-specific rate of cancer occurrence. And yet in the earlier days when the strains of mice were not so, when they would concentrate on using strains that had high cancer rates, people seem to see cardiovascular effects also. And this, I think, is a very important point, which has been lost sight of in recent years. and that comes back to the point of the difference between partial body radiation and whole body radiation. You know, that was discovered very early at the people working at the University of Chicago, that you could shield part of the body and you could change the lethality dose of radiation. So there are hormonal effects that result from the radiation. And again, we come back to the problem of the time in the development of a science at which you do a particular kind of work. All of the work that had to do specifically with endocrine organ exposure to cancer were done with high doses because there was no way to measure the hormonal changes easily. These were developed by Rosalind Yallow and her colleagues much later in radioimmunoassay. So the work, if one goes back into the literature and searches for effects on specific endocrine organs, all the doses were very high. Nothing was done with low doses because we couldn't expect to find it. We didn't have the means to find it, except for thyroid. You remember Dr. Firth here worked a lot with thyroid cancers.
Oh, yeah.
And showed numerous ways to affect the incidence of thyroid cancer from a given dose of whole body radiation. But that work has not been followed up. It's been largely ignored by later workers who've been more interested in the target theory or approach to what happens. So we have lost sight of this effect, which is also one of the ways you measure. I think almost everybody is familiar with the fact that if you get a fairly good dose of radiation to your head or abdomen, you get nauseated. Mm-hmm. And my thought
by
about
fairly good dose, you mean?
Well, this is in
300 or 400 rads.
You always get it with that.
Yeah.
But 50 rads
Even 50.
is quite frequent. And if you look at the statistics of the thing, it's somewhere between 1 and 40 or 50 rads. It would be almost sure to give you nausea. Maybe as low as 1 rad.
Is that right?
And this certainly has to be a hormonal effect. Mm-hmm. And my thought is that it affects the appetite and satiety centers in the hypothalamus and the lower part of the brain. And it tells you, this is a hypothesis that I've been developing, tells you that you have eaten too much.
Oh, yeah.
When you get a dose of radiation.
Uh-huh.
And you get nauseated. You don't want to eat. That's the main thing.
Oh, yeah.
The result of it. Because the body has been fooled into believing that it's had an overdose of food.
Oh, yes.
And I can't prove that, of course, but I think it's correct because there was an experiment done by physicists working at the University of Chicago in around 1950, and with Leon Jacobson, who later became dean of the medical school at Chicago.
Oh, yeah.
And some of their other colleagues, in which they exposed mice to gamma radiation from radium. Mm-hmm. And they found, to their very great surprise, that the ones that received 1/10 of a rad a day, whole body radiation, gamma rays, lived longer than the controls. Mm-hmm. And those that...
See, a 10th of a rad, that's 100.
That's 100 millirads a day.
100 millirads.
110, actually, is what they received. And those that received 1,100, 10 times that dose, didn't have a shorter life. Some had a little bit longer life, and some had a little bit shorter life, but their median age of death was about the same. Mm-hmm. And those that received higher doses, say 220, 2,200 a day, did live a shorter life. They had their life shortened, just as you mentioned a while ago. Mm-hmm. And there were extra cancers. The cancer rate was higher, but not much was said about the other things, except they did some chemical work on the carcasses of the animals after they were dead, and found that the fat was low. Fat content was low in the carcasses, in the radiated animals.
Now this was actually amounts of say only 2,000 millirads.
Yes.
That's good. And I can remember in the work of Upton, when he performed his experiments, on genetic effects, life shortening, and cancer production, I guess, and so forth, that he was using much higher dosage, something like 50 to 500 rads, which is way out of this range.
Most of them were like that. These were single exposures, though, and remember that the Chicago experiment I'm talking about was a continuous exposure.
Mm-hmm.
It was so that the animals absorbed as much or were exposed to as much as several hundred rads before they died.
Oh yes. Mm-hmm.
And of course, it was partly on the basis of that the Upton experiment was set up.
Oh yes.
And the people who were concerned with the planning the Upton experiment, were quite a large number of people involved, calculated the number of animals they would have to have for single exposures of a few rads, and decided that there was not either the money or the facilities to handle that large number of animals.
Mm-hmm.
So that's why the doses were higher. There was one set of 10 rad exposures.
Mm-hmm.
And the very interesting thing about those, they lived on average exactly the same as those who received no radiation. Now, this is 10,000 millirads at a single exposure. But the lives of a few were shortened a little, and the lives of a few were lengthened a little, so that the average turned out exactly the same as the controls.
Yes.
Now, I think this kind of confirms the experiment done by Lorenz and his collaborators at Chicago, in a way. But a curious thing about the Chicago experiment is that because they exposed the animals in a room that had radium in it, they could never leave the controls in that same room. Controls had to go in a different room.
Mm-hmm.
And a lot of people have said then, this is no experiment, you have no control. And so we will throw that experiment away. It's no good. Because a few other investigators have been unable to duplicate that experiment.
I see.
And that others have been able to duplicate it. And what has happened, very unfortunate, I think, from the standpoint of the development of radiobiology, is that people chose to discredit the experiment rather than trying to find out why there was a discrepancy between different laboratories. This was a terrible mistake in the long run, because it will cost us enormously in misunderstanding of the cancer problem and of the radiation problem, both.
Well, let's see now. How would you summarize then the effect of the Lorenz experiment and its meaning?
I can give you my explanation of it, but you must understand that many people don't agree with it.
Yes.
My interpretation is that the low doses of whole body radiation, the effect on the endocrine glands was larger than any effect of cancer induction. And what happened was that these animals were discouraged from eating because their satiety and appetite centers were affected by the radiation.
And now by the low dose, how do we
dose.
define that? Say 10 rads, or what do we call the low dose there?
Well, the low dose is the 110 millirads to 1,100 millirads per day would be the low dose.
Yeah.
I say the endocrine effect was larger than any deleterious effect of the radiation.
Yes.
and it reduced the food intake of the animals, and because of that, they lived long.
Yes, all right.
Now, it may have increased.
But they were given daily dosage, so that
That's
the
right.
accumulated dosage
It's very large.
was very large.
Yes.
If you gave one rad, or that would be 1,000 millirads over a period of a month. That would be
you have
30,000
30,000 millirads.
millirads. Yeah. So, but I'm sorry, I interrupted there. Now what comes back to the effect now on the result of that, and what your interpretation is.
Yes, well, I think when you go high enough in the exposure, and by this you'd probably begin with a single dose exposure of over 10 rads, 10,000 millirads, somewhere above that. Then the deleterious effect on cancer and perhaps on cardiovascular disease exceeds any effect that can be induced by a change in appetite.
Oh, yes.
And so that's what you see. You don't see the other effects. When you go to these lower doses, and the point, I think the point to be made about that is that we could estimate the internal dose, which would be equivalent to, let me back up a moment. What I want to say is that the food produces the same kinds of radicals that radiation produces. And that's why the body mistakes the radiation effect for a food effect.
Oh, yeah.
So we can tell then by the type of experiment that was done by Lorentz how much of those radicals are produced by food daily or ordinarily without any exposure to radiation. And it looks as if in the mouse it's almost exactly equivalent to 1 rad a day, 1,000 millirads a day. That is the effect of food, because those animals, you see, did not have their lifespan changed. Their median lifespan was the same. You could expose them to that much rad a day continuously, and it wouldn't affect them. I shouldn't say that's equal to the internal dose. That means that the dose from 1 rad a day is so much less than the dose you get from food that it has no effect.
Oh, yes.
You could think back, make a comparison. That almost everybody who's worked in radiobiology has started out believing that the only kinds of radicals the body sees are those produced by external radiation and internal radiation that we call background. And that's something like 100 or 200 millirads a year.
Oh, yeah.
But actually, we see a far, far higher number of those radicals from the food we eat. And if you impose a dose of radiation on top of what we normally get from ourselves, not radiation, but the radicals that are produced by radiation, if we impose an external dose, then it's a fraction of the total dose that's represented by those that is the increment of damage. It's a little damage piled on a lot that we're already handling. And it is not equivalent to the background radiation. It's equivalent to hundreds of times the background radiation. And so I think it's silly of people to look only at background radiation as the background which we normally suffer. That's only a minute part of it. But the reason people don't accept that and don't pay much attention to this possibility is that there's no way to measure that flux in the body, the flux of real radicals, because there's no method that is sensitive enough to pick it up. You could not measure chemically the effects of 10 or 100 rads of exposure by looking at the tissues of the body.
Mm-hmm.
And so we can't see that. The nearest we have to a method is electron spin resonance, and that is limited by the fact that the water boils it. So in the presence of water, you can't measure that very sensitively. But there are people working out trying to measure indirectly, and you can measure it indirectly in several ways. And the flux is the flux of radicals produced from just metabolism of food is large enough to be equivalent to some matter of rads a day of external exposure.
Mm-hmm. Well, then, so as I say, this experimentally, this is a very difficult field then to investigate. And well, now, with regard to this, then, when we come to examine differences naturally occurring, say, between sea level and, say, Denver and so forth, we'll get 100 MR difference in annual exposure and so forth. This doesn't lie within probably realm of being able to really see whether it has a beneficial effect or a deleterious effect.
That
it's
difference
so small
is
that you won't
by
ever,
the internal.
It's swamped by internal internal things. So you need much greater things. So and therefore, because this brings up the alarming response that people get to the minute traces that fell out from Chernobyl, say in the Arctic, where the reindeer are now getting 5 or 10 more millirems than they would normally get, and they feel that this will increase through the food chain up to double or treble that, but it still is so small compared to...
You could miss a meal and handle all of that stuff.
Yeah,
just by missing one meal.
Missing a meal would would wash out the whole effect on this. So actually, studies of that type are likely to be at best misleading and even perhaps worthless.
It's a terrible thing, Clarence, that we spend so much money on that kind of thing, because that's diverting money from other very worthy causes that have no difficulty like that with them. And this is a matter of great concern to me, and I hope becomes to other people, that we can get back on the track to really understanding this. There's almost no work supported now that relates radiation to endocrine function. And you cannot get it through the study section at the National Institutes of Health. And now there was one person who was interested in that, and this story is interesting because it amplifies my worry about the narrowness of each individual's concentration in science on some specific problem. We've lost a lot of the generalness of science by concentrating so heavily, and of course concentrating heavily in a narrow area does produce fantastic results, but somebody has to be back there to put all the narrow fields together somewhere along the way, and we lack that pretty badly. Tom Doherty, you remember, was in charge of the Utah project out there. Tom Doherty was an endocrinologist. He was an endocrine biochemist, really.
Oh, yeah.
And he noticed also this, or was interested in the white cell reduction following whole body radiation, because he had studied stress. And one of the signs of stress was a reduction in the white cell.
Mm-hmm.
And that's perfectly well known that a little bit of cortisone or something like that will reduce the white cells, stimulate the adrenals, and the white cells go down. And he told me many years ago that he thought that the small dose of whole body radiation was just the stress on the body, which affected the adrenals and caused the reduction in white cells. But white cells are sensitive to radiation, and most people believe that they're killed, and that's why they go down. They don't believe in the endocrine effect there. Mm-hmm. Now, he's the only one I know of who used relatively low doses of radiation and tried to study their effect. No one else. All of the other endocrine work with radiation that I know of starts at around the 500 rad level.
Oh, yeah, 500,000.
Completely out of range of where one should work. Mm-hmm. And if you ask a radiobiologist now, he'll say, oh, well, those experiments were tried and they didn't find anything. The reason was they were not working with sensitive enough methods, and they were using far too much radiation. Those things all need to be done again, because the methods for detecting endocrine changes are now very much more sensitive than they ever were before. Mm-hmm. So, and Doherty was convinced that we were overlooking something like that, but he was not in the position apparently to continue carrying on the work out there. They had a mission which was quite different from that. Mm-hmm. That was to study effect of fission products, as you recall. Yeah. So, and he died a number of years ago. So far as I know, he's the only radiobiologist who really believed that we should look at the endocrine effects of whole body radiation.
Now, when it comes to these various levels of exposures, we had a wonderful opportunity to study this in the Hiroshima and Nagasaki studies, and in newspaper accounts, in general accounts, there's a good deal of misinformation or lack of information, or taking little pieces of the data, and so seems to be a lot of confusion in the interpretation of these things. And when I have looked over some of these studies, I think was the latest one I had access to is a 1977 tabulation, and there were several things that, if you examined it very carefully, it stood out. If you take the cohorts which had lower levels, like below 100 rad or below 200 rad or something, or below 50 rad and so forth, and examined the number of deaths from cancer and these various things, you got a very confusing picture. And depending on what cohort, it was very evident. Like, I don't know, one of them, let's call it the 0 to 50 or the 0 to 100, something like that. That showed seemed to be a protection against cancer among and then when you, of course, got over the 200, of course, the damage, there was an increase in there. And then if you take out, the population as a whole and just examined death and non-death, there seemed to be fewer people dying who have been exposed, just taking the population as a whole, as compared to the controls. And so there's an awful lot of confusion, and you can almost pick out different cohorts improve different things. And I was wondering if you had any general feeling for, has there been real sense made of this, and what are the conclusions?
Well, I think you've described the situation as most people see it pretty well. Those who believe that the low doses, the effects are under, what should I say, that we underestimate the effects at low doses, mm-hmm. have a scenario for explaining why. They don't see the deaths, so they create them with a pencil and paper. And they do it in the following fashion. They say there's a 5-year gap between the real systematic setup of the Atomic Bomb Casualty Commission and the atomic bomb. Mm-hmm. And they say that the people who were traumatized by the bomb, the survivors, the weaker ones died because of their exposure to various other things mm-hmm. besides radiation. Mm-hmm. And so that only the stronger ones are present, and that's mm-hmm. why mm-hmm. You don't see much effect at low doses, because the population is not representative of the original population. And my interpretation would be exactly the opposite of that. So I can create I can save these people with pencil and paper just this way. Mm-hmm. They kill them with pencil and paper. If my idea is correct about the endocrine effect, one of those effects is that if your body believes you've had too much food, it's you have a short life. When you restrict the food, the life is lengthened. So it's reasonable to say that if you give too much food, it's shortened, or if you give as much food as they would like to eat, it's shortened. But that really the susceptibility to cancer and the susceptibility to cardiovascular disease are genetic things that interact with the environment. And one of the things that happens when you have plenty of food is that you live a short life and you die from cardiovascular disease. And you die early from mm-hmm. cardiovascular disease. That reduces the next generation because these people have not time enough to reproduce fully. Yes. They die too young. And that's what happened. The ones that were exposed to small doses of radiation, the body interpreted this as extra food, and they died of cardiovascular disease, so that we have left cohort which is richer in those who are going to die of cancer.
Oh, yes.
And this is just the opposite of what they say. Yeah. So I can argue that the effect we're seeing is less than we should, is more than we should see. That is, that there should be a greater protective effect at low dose. Mm-hmm. And instead of having a curve which is high at low doses, we have one that should be even lower. Oh, so there's no way we can objectively decide between these two things. So they both should be thrown out. Oh, yeah. So what we see is exactly about right. Mm-hmm. We see no effect below about 50 rads of dose, and above that we begin to see the extra cancers that you expect. And
but right along with that, there seems to be a lower mortality overall. As I remember the numbers, at one point, say in 1977, there were, say, you would expect, say, 22,000 deaths in this particular 35-year period or whatever it is. And there were only 2,000 deaths.
Well, that's consistent with my interpretation. These people got extra food. I mean, were fooled into believing they had extra food, so they didn't eat as much later, and they should live longer. Uh-huh. So the rate should be a little lower. Mm-hmm. And what
primarily because they eat less, and therefore their diet was more optimum to their long range survival.
there's a terrible narrowness about people who are concerned working with cancer and those who are concerned with working with something else. It's the narrowness I was talking about a while ago. I have a book in there produced by the U.S. Public Health Service, about so big, weighs 15 pounds, and it is about cancer. And nowhere in that book can you find a word about the rate of cardiovascular deaths in those populations that are being studied. And a familiar instance is talking about Utah, which has the lowest cancer rate of any state in the continental United States. And nowhere does anybody say they also have the lowest cardiovascular death rate. Nowhere can you find that. But it's true. They do. And it's lower in proportion to the total death rate in exactly the same proportion that cancer is lower. So I say this is an inherited factor. And when one is low, the other is low. So what people should be following when they look at the atomic bomb casualties is both causes of death. One should look at cancer in relation to cardiovascular death. And what you're saying a moment ago, they don't die as often. They're lower on cardiovascular death. Because that's the main thing that fixes the lifespan. So we make terrible mistakes in not looking at the boundaries of, or extending the boundaries of what we look at. I believe people would have a totally different conception of cancer if they always linked it to the cardiovascular rates that occurred in the same population.
Yes, of course, this is a little bit aside from our discussion, but of course, in our civilization, the horror of a child or a person having to go without a meal, is just something which, how could any civilization be so cruel as to inflict that, on this? And, in my interviews of people who grew up particularly during the Depression, including myself, money was so scarce that one common way of saving money was to eat 2 meals a day. And you'd be surprised. There were at least 4 Nobel Prize winners who, in that particular period, saved money by eating 2 meals a day. They're now all in their 80s. So there are all kinds of these factors which enter into lifespan, and so it gets so confusing.
That's a particularly good one that you just mentioned, because I've looked for information on our average food intake during the Depression, and the best I can find, one survey was made, and it was about 10% lower on the average than on either side of the Depression. So the people who were born during the decade from 1930 to 1940 are just now beginning to die at a fairly good rate. And in the next 2 decades, we'll find out if they, on the average, live longer than the people before. And I think they will. I think
Well, that's rather interesting, because it was very common. And then among all of the schools, the graduate school students and college students, they all had that same problem of trying to live on $30 and $40 a month during those days. And as they say, there are very famous people here.
And people talk about the baby boom. Actually, this lack of food during the Depression is part of the reason for the reduction in birth rate. And the baby boom is the return to the birth rate that they had before the Depression. And one can find other populations that were starved, like the Netherlands population, I think in 44.
Oh, yeah.
The birth rate dropped to 0
Oh, yeah.
while they were in that famine.
Oh, yeah.
And then it returned promptly after the famine was over.
Oh, yeah.
So I think they should talk about the birth rate depression rather than the baby boom.
Yes, that's a very good point. Now, well, with regard to other investigations that you're in at the time, I wanted you to get a little discussion on this subject of hormesis. Is that the way to pronounce it?
Yes.
And number one, will you define the term? At least in one dictionary, I didn't even find it.
Well,
But what is the definition?
Well, the
of
definition of hormesis is the effect that a toxic agent has at low doses that seems to stimulate something. Arsenic is a very good example of it. Low doses of arsenic are quite stimulating to people and to horses. Many a horse trader made his money by feeding his horses arsenic just before he traded them.
Oh, yeah.
And their coat gets sleeker, they look healthier, and they act more active. But of course, if you give more, it kills them.
Oh, yeah.
But that low dose effect of toxic agents to improve things, to seem to improve things, is called hormesis.
Oh, yes. All right. Fine.
And we've already discussed it to some extent because the experiments of Lorenz were the first example in animals of a hormetic effect of radiation. The lengthening of the life is regarded as a hormetic effect.
Yes. I believe that there are quite a number in nutrition. Like I believe cobalt among the sheep in Australia or something. I think they found that there were certain areas that were low in cobalt, and it was very deleterious. And when they added cobalt to the feed, it was
there's a very interesting story about that. I don't know whether you remember Perry Stout.
Oh, yes, I know him.
He was
very
the
well.
one who showed him how to cure that cobalt deficiency.
Oh, is that right? I did not know.
He told them to use the knurled nuts that you have on crescent wrenches, the little thing. That's a cobalt-containing steel.
Yes.
Those wrenches are made of, and that little nut. They poked it down the throat of the sheep, and it stays in the forestomach.
Oh, yeah.
And it doesn't get lost. It doesn't get out of there, and it slowly erodes and frees the cobalt at the rate about the rate the sheep
about
need.
The rate that he, so they don't have to keep adding it.
No.
Well, that's fantastic. And then I believe, at least there's a fad now that adding selenium is good for food.
Yes,
I don't know whether that's considered a fad now or whether it's...
Well, it is a fad because the fad people have picked it up.
Yeah.
That's a nutritional fad. I worked with selenium when I was an undergraduate. I was at Wyoming where selenium toxicity was very bad.
Of course, the toxicity is very bad.
Yeah.
But is there a small amount which is...
Small amount because it is required for... It's very interesting how that fits into the discussion. It's required for a peroxidase, which oxidizes reduced glutathione with hydrogen peroxide. It's a requirement for that enzyme, and that enzyme is what reduces the last traces of radicals in places where they're not wanted, because the radicals will affect glutathione, and so the selenium actually reduces the free radicals that I think are the root cause of cancer.
Well, that, and then of course, I guess like things like vitamin D, overdoses of vitamin D can kill you, have killed children, and of course, well, we need a certain amount. So there are a lot, but the hormesis effect of radiation is there seems to be some evidence, but there's not enough work really to really define it. And I might ask a question of you, for instance, if you had your choice of living in an entirely free, it'd be impossible, but entirely free radiation from birth, or one which had normal radiation, which would you choose?
I think there's nothing to choose between these, and that brings the point of importance about the definition of hormesis that I didn't touch on. Now, the person who is promoting hormesis mostly in this country believes that it is required, that radiation is required for the body, that it is a nutritive to the body. What I am claiming is a little different. It's that radiation fools the body into believing that it has received nutrition.
I see. Your mechanism is a little different from that.
And I think that that the bad repute that it has comes from the idea that it is nutritive. And so I try to combat that idea and say, no, it just fools the body into believing it has had some food.
Oh, yes.
And I believe people would accept that easier than they would accept that nutrition was good, that
radiation was good for people. So, so that, in other words, you don't think that if a person had a choice between living in an absolutely free radiation atmosphere for his life, he wouldn't necessarily suffer from it.
I don't think he would, but there is a school of thought that thinks that quite possibly the random radiation effects have something to do with the biological clocks, setting the biological clocks.
Yeah.
And I have no particular strong opinion about that, but I doubt it. It was one of the first things that was suggested for effective radiation, and it was shown to be wrong in that particular instance. But it's still a possibility that it has something to do with setting clocks.
Yes. Well, the natural radioactivity of potassium was thought at once to have some role in the heart.
Yes, that's the one I was speaking of.
Was that the one you were speaking of? Fine. Okay. Well, let's see. Now, how would you summarize now there? We can start in now with your present writings and investigations and so forth. What is your present main interests?
Well, I'm trying to learn enough about demographic techniques to show by some methods which people perhaps haven't thought of or haven't tried that there is no real change in incidence of cancer over the years. I guess that's a little bit the wrong way to say it. What I'm trying to show is that cancer is a normal cause of death, and it is inherited in the same fashion as other causes of death in old age, like cardiovascular disease. That is, we have a certain amount of energy which we get from our food, and a certain rate at which we can use the energy, and it's used for what purposes? It keeps us warm. It enables us to find more food, to exercise, to work. It enables us to reproduce. And part of it is used for maintenance of our body so that these functions will go on. And we, by natural selection, always tend to increase in efficiency because we compete with other creatures or each other for the use of the available food. And there's currently a pretty strong belief that the reason we age and die, is because it's more efficient in the long run for that to happen than to try to use so much energy for maintenance that we live forever.
Mm-hmm.
And you can very easily show thermodynamically that that's true.
Mm-hmm.
That it's better to make new people than it is to try to keep the old ones
Oh,
going.
yes. Mm-hmm.
So I believe that the whole thing is very rationally worked out, and that we'll find that cancer is just another part of that system. And what I want to be able to show is that you cannot interpret cancer as an accidental cause of death. The vast majority of it. A small amount, perhaps, but it'll be very small. And
Perhaps less than 1% or something like that.
Yeah, something like that. In special cases, maybe 4 or 5%, but normally 1% or less. I can't find incontrovertible proof of that yet, but that's what I'm shooting for.
Oh, yes. Mm-hmm.
Now, when I try to talk to people who are interested in cancer or about natural selection, they think I'm crazy. It's almost impossible to get them to think of this in terms, because they believe that the bell-shaped curve, which represents our rate of dying, the frequency of dying, it's not a normal curve in most cases. It's a distorted normal curve. And I'm saying that if we were living in a neutral environment, it would be normal. And the fact that it's distorted shows that we're being selected very rapidly for a different longevity. And that's why the curve is not normal. But if it is a normal curve, or supposed to be a normal curve in a neutral environment, there are two ways to look at it. One is that the variance is due entirely to the environment. We all inherit a specific lifetime, and the varying environment produces the bell shape of the curve. And I believe that it's commonly accepted among cancer researchers that that's the case, that it's all due to the environment. You inherit a specific lifetime, and everybody inherits the same one. That seems silly to me. Most of the variance in that curve is heritable, I think. And it's over this point of whether our lifespan is largely heritable or largely environmental, because is the crux of the argument. Now, I think it's very easy to show that much of it must be heritable. And to talk to population biologists, I think you'd get no argument. But they never talk to the cancer people, and the cancer people never talk to them. And that's the difficulty.
Yes. Well, now, of course, the cancer people are overwhelmed by the environmental factor of smoking, of course, which is that's such a big and unusual thing, and probably it is it's disputed as to how big the factor is, but undoubtedly it is a big perturbation in there. But otherwise, what are some other environmental factors which supposedly increase cancer rate or affect cancer rate, the environmental?
Well, it's perfectly clear, I guess, that environment affects specific cancers. Now, there's no question that we have dropped in our number of stomach cancers. And I'm not even sure that smoking hasn't done part of that. But that raises, if you suggest that, raises an immediate howl of protest. Because smoking affects the motility of the stomach. And it reduces tension. And tension may be cause of acid production, which eventually may be the cause of stomach cancer. So you can make out a possible scenario for that. But irrespective of that, while the lung cancer goes up, the stomach cancer goes down until it's nearly disappeared. And people will not connect those two things. They absolutely refuse to, because they think that the environment produces accidental cancers one way or another. And anyone that goes down, you're just lucky because you've changed the environment in some way you don't know about. But if cancer susceptibility is inherited, then if one cancer goes up, another one has to go down, or some others have to go down, because you're inheriting. You have 20% of the people can die of cancer, let's say. Well, if you get a lot of lung cancers, then the other cancers must be less than that to make the 20%. But if we're dependent upon an oncogene scattered somewhere in our tissues, and we can't have a cancer unless there's an oncogene there. All right, changing the environment is not going to affect the people that don't have the oncogene. But some of them, it's like blood groups, some of them inherit the oncogene for colon cancer and some don't. And I don't know what causes the stimulation or gets those to change to become active. And it may be something like people think. I'm inclined to doubt the target theory even for that. But simply because I think it's misled us in other respects. But if there is such a thing as cancer in one spot, withdrawing general resistance to cancer in some fashion, not just local, but general, then having one cancer affects the rates of other cancers. And so I'm trying to think of that, but what I'm mostly trying to do is not settle on any hypothesis that will channel my thinking as the way I believe others have channeled theirs, so they can't get out of the hypothesis that's no good.
Yeah, it's that your microphone just dropped out of that socket. But now come back to press it on. Come back to that theme. There's of course been a lot of pressure in recent years about the synthetic things that are put into our atmosphere and the food chain, the insecticides, some things that are put into soil so there are all kinds of new sources of our carcinogenic compounds, particularly in insecticides and herbicides and so forth. So now large stores now advertise, organic grown. And Bruce Ames has pointed out that natural, in order for a plant to survive through evolution, it has had to synthesize its own insecticides in order to survive against insects. And in many cases, those insecticides are just as carcinogenic as synthetic ones, and perhaps more so because you can sometimes tailor them to avoid these. And I was wondering if you had any general feeling about these things that we add to the environment to avoid carcinogens. How would you classify the various things and their dangers?
Well, I'm quite sure we're overly concerned for the short term, but we should be concerned for the long term. We have to know what these things do and how fast they leave and so forth. And we don't do that well enough. I went through that experience myself on our farm when I was boy, I used to help spray for the cotton bollworm.
Oh, yeah.
And the first thing that we could get a hold of was lead arsenate. That killed the worms all right if you got it there fast enough.
Oh, yes.
But years later, when we tried to grow cantaloupe, there was too much arsenic in the soil.
Yeah.
So
there's arsenic, copper arsenate was very common.
Used, yeah, in the old
common.
days.
The Paris green. Green was due to the,
we had
copper.
We kept a pound or two of that around all the time when I was a boy, and I was warned against how poisonous it was.
Yes, and so of course, but these modern ones usually don't have metals, the toxic metals, metals in them, and are synthesized in such a way. Of course, actually, I believe there are certain carcinogens in what is it, mushrooms and in peanuts and so forth that are they're natural. They're very.
And Bruce's point is that we probably owe most of our cancer to those, but I think he's coming more around to my point of view that it's internal and not from external agents that we get them.
Oh yes.
I think that we owe the fact that we have to have cancer to the economy of nature. We could avoid that cancer, but we would lose something else that we have to have if we did. And so it's cheaper to have the cancer than it is to build a wall against other things. And the thing that it's a very simple proposition, and any thermodynamicist would tell you something like this has to be correct. That if you had to produce the proteins, enzymes to combat all of these things that Bruce Ames was talking about, it would be more expensive than having a few cancers. So you allow enough of those radicals to escape destruction, so that you can use them to destroy these strange compounds that come in. And that's exactly the way it is. The peroxidases, you see, are all produce those radicals. And the advantage of a radical is nonspecific. It will attack anything organic. And you do not have to have a specific enzyme for it. A peroxidase is a very nonspecific enzyme. But a trypsin or a chymotrypsin is a very, very specific enzyme. It will only work on a certain kind of bond. And so the balance of nature makes you produce both kinds of these things because it's energetically more economical to do it that way. And so if the people who are seeking a complete prevention of cancer are probably going to kill us all.
Oh yes.
if they ever find something like that. And I think that we do not take into consideration enough what the real economy of nature is.
Yes, well, of course, actually, I don't know what the exact figures are, but you hear these figures bandied about. In the last 50 years, we've probably increased the lifespan of people 15 to 20 years. It's throwing our Social Security plans all out of whack and everything else. And, of course, that gradually is going to reach a plateau, of course. But there's no doubt about it. It's being a fantastic increase in the lifespan in the last 40 or 50 years. And so it isn't exactly that the appearance of chemicals and radiation are killing our people off at a great rate. The numbers just don't bear that out.
Well, this brings up another point that I might make with you. You talk about increasing the lifespan, and we get this from the life expectancy tables, and that's perfectly true. But if you look at what the maximum life lifespan is.
Mm-hmm.
Well, let me back up a moment. The Cancer Institute people will tell you that people who are working with the demographic figures, that cancer in men has increased, or I should say the age-adjusted rate for cancer in men has increased a lot. For women, it has gone down slightly. And if you look at the real data, the fact is that the fraction of people dying is the same in both sexes.
Oh, is that right?
Yeah. No one ever tells you about this.
I'll do that.
And the reason, the odd reason that the men are going up, age adjusted, and women are going down, is because women have actually increased their lifespan. Men have not. And so their cancer spread over a larger number of years, and the rate is down. And so the fraction stays the same.
Fraction stays the same.
Yeah. So these are the kinds of crazy things.
You really have to examine the figures.
You have to look at
carefully in order to come to a logical conclusion on these things. So that's very important. Incidentally, I happened to think, how do your views on radiation coincide with our mutual friend Merrill Eisenbud? Merrill's been working in this field of radiation for a long time.
Merrill's a pretty sound scientist, but I haven't talked to him for a long time, but I'm sure he's much less concerned about the cancer than other people are in radiation. Is that correct?
Oh yes, that's right. In fact,
so they probably do coincide.
He's very concerned about the irrational fear of cancer and these extremes that are being used to clean up these minute traces of radioactive materials, spilled uranium and so forth, and so on, which is entirely non-productive use of money.
That's the biggest problem that faces us for the next few decades. I often wonder whether the people who are doing these things have a real hidden agenda. Everyone knows that the problem comes because there are so many people. And we also know, I think realists don't believe that you can change that.
That's right.
But the others, some of them may be trying these things just to bring us to the edge of some kind of a catastrophe to reduce the population. I wonder how many of them know that they're doing this, and how many of them are doing it because they have a single track mind and only think of one thing at a time.
Oh yeah. Well, it gets to be very discouraging. I see some of these things. The cleanups, there's going to cost $22 billion to do this and so forth. At the most, it might possibly save one life, although there'll probably be about 20 lives killed by bulldozers and so forth in doing this.
Sure, the cleanup will kill more.
And there's this sort of an insanity that's going on in these extreme things. But we're right in the middle of it, and it's apparently has great momentum. And of course, there's also a selfish standpoint. When the Great Society proposed the poverty programs, the hue and cry of all the sociologists coming to Washington, there's money in poverty, was the great cry of the times. Today, there's money in scaring people to death, and that money is getting in billions and billions more all the time, and that undoubtedly affects the thinking of people on this, and so we're faced with trying to get some rationality into hazards of all type, radiation, chemicals, insecticides and so forth and so on. But
it looks like
it's no very simple problem.
Fighting a losing battle too,
Yeah.
because what you're saying basically is to get people to think more quantitatively, and yet the arithmetic
Yeah.
is going down in the schools, not improving.
That's right. And then of course the arithmetic, very little arithmetic incorporates the concepts of statistics and probabilities into them these days, and which is the two basic things that we use all our life in order to evaluate the meaning of numbers. But that's left out. But incidentally, who is in the Washington area? Who are some of the more sensible people involved in statistics or biometry and so forth and so on these days? Do you know any?
Well, the best statistician that I know of in the National Cancer Institute are Nathan Mantell, and if he's still active, and the epidemiologist. They have a good epidemiologist there, but I'm not sure he is still active. I can't think of his name now. Mm-hmm. But these are not the people who determine what is said by there. Now, there is an ex-member who I think is way off, and that was Marvin Schneiderman. Mm-hmm. Now, he believes in, as John Baylor believes in the age-adjusted values for cancer, which are really very misleading and should be abolished.
Oh, yes. Mm-hmm.
So Marvin Schneiderman is still active, but he's no longer with the National Cancer Institute.
Oh, yes.
He's a good statistician, but he's an awful poor biologist.
Oh, yes.
I think that's the problem.
And you have to tie those together in order to get some very good, sound opinions.
I don't know the real answer to that question, but almost nothing that comes out of the American Cancer Society or the National Cancer Institute for the public's consumption, or even out of the National Academy of Science. Their nutrition book on cancer is pretty bad.
Yes. Well, that brings me to the final subject that I wanted to ask you about, and that is this book that was put out by the National Academy on radon. Did you?
I haven't seen it.
Yeah, it's a fairly thick book, maybe 300 pages or something like that, and it's not very easy reading because it's got a lot of collection of different things. It's awfully hard to find, but apparently out of that book came this statement, that where we have 2,000 deaths per year from radon.
That's crazy.
And that is such a crazy statement. So I went into the book, tried to find the rationale. The book doesn't have the data or the facts in there. And I was wondering have you come into any discussions as to how they arrived at what the data is? And
well,
so
I know a little bit about the original background, but I don't know much about anything recent.
Yeah.
And again, I like to call on Barry Stout for pointing out what's the matter with that problem.
Oh, yes.
He says he'd looked very carefully at the lifespans and so forth, or what he could find out about them, of burrowing animals who live in a much higher radon concentration than we do. And he never found any lung cancers in any burrowing animals.
That's an interesting
But there are burrowing animals, that live in those tailings deposits where the radon concentration must be awful high in them.
Oh, yeah.
And they maintain a population without any trouble at all. So,
oh, yes.
I think this is biological knowledge enough to be skeptical about anything said about radon and lung cancer in an ordinary population.
Of course, one of the things that really bothers you is that they sell these kits, and they're millions of dollars worth of these kits. Everybody was buying a kit, putting them in a corner of the basement, and they put them there, right where it'd be a stagnant area, right in the corner of a basement, where
nothing moves,
where nothing moves, and so
nobody
forth.
gets to,
and nobody ever gets to, and then they take the readings there. Well, the reading should be taken in the average living space of there, and I would bet that for every 100 positive readings that you'd get by the basement, you'd get only one in the living space.
It would be something like that.
Yeah, and right. So I would say, just as a start of that, if there is any effect whatsoever, they're probably 100 to 1 off on the thing.
I tell you what you might do, just for your amusement sometime along that line. The fellow who's really behind all the present scurry about radon is that fellow Archer, who had charge. Archer and Linden, I think, was the original pair that had charge of the USPHS's radon studies. Archer has written a paper somewhere about 82 or 3 in the Nuclear Safety Journal of Nuclear Safety. I think you're familiar with it. It's published here.
Oh, yeah.
Bill Cottrell used
to be the editor. He was the editor for a long time.
It's right next to one of mine in there, and I don't think anybody ever sees that journal outside of the very specific people involved in nuclear reactor safety. Which you do well to read, because it tells you kind of what makes Archer tick.
Oh, yeah.
It's a statistical study of background and various diseases. And it's absolutely a weird story. And if you look at that, it'll give you an idea of how to judge the architect of the whole radon problem.
Oh, yes.
I don't know whether this should go on your track or not, but there was a lot of politics involved in that before you came to Washington, and it antedated me quite a bit.
This is edited, so this is the tape.
If you don't
edited,
like it on there, take
whatever
it
it is.
Yeah, okay. And it really started. The real trouble started in '59. It's when that industrialist from California, I think, was chairman of the AEC. What was his name?
That was before Seaborg.
Just before Seaborg. He's only there for a year or so.
Yeah.
But doesn't matter. Yeah. I don't think he was at fault.
Yeah.
But it happened under him, I think, because the production people and the reactor people felt that the biologists were cutting in on their promotion because they made everything look unsafe. And so they decided to get the biology out of the AEC. And he found out rather quickly that there had to be an internal safety operation. So they split the biology division into operational safety and biology research. And then they said biology research should go to USPHS. And they were far along on their dickering, and the Bureau of Rad Health was created out of a cadre of unemployed or nearly unemployed uniform personnel in USPHS. And they expected to inherit the $80 million or so. But all of a sudden, the Joint Committee stepped in and said, "You can't do this. They don't have any competence. You better keep that in the AEC." And that's what saved the research program for when Seaborg came. But then the Congress told us that we had to get together with this Bureau of Rad Health and had to do things jointly. But all they were interested in was taking the good part of our program and letting the part they didn't want go. And it was a political thing from then on. They wanted our money.
Oh, yes.
And the way they tried to get it was to back sub rosa, I think largely, the claims of everybody who was anti-AEC.
Oh, yes. Mm-hmm.
Now, I know that happened because when Goffman went off fired his rocket,
Yeah.
I talked to the deputy director, who was a neighbor of ours,
Mm-hmm.
of Bureau of Rad Hill, and I talked at some length about. I frankly thought Goffman was off his rocker. He'd blown a gasket. And within 24 hours, Goffman knew everything I'd said.
I'll be there.
And that came to me through, I think, one of the deans of Minnesota who heard Goffman's talk shortly after that, in which he quoted a number of things that I had said to this member
Mm-hmm.
of the Bureau of Rad Hill.
Mm-hmm.
So, and he sent me a transcript. They tape recorded the talk. And I recognized these things that I said across my back fence.
Mm-hmm. I'll be there.
So I sent a copy of the transcript to that guy.
Oh.
He wrote a long letter of apology and a letter to Goffman saying, "Oh, Totter didn't really mean these things."
Yeah.
But that's what has happened all along. There's really only been one or two people in there who refused to attack everything the AEC did because they were sounder scientists than the others. They were not politicians.
Yeah.
And Billy Mills was one of those.
Yeah.
He'd taken his training with Cyril Komar.
Mm-hmm.
And he never joined in that. But most of them were dead set on undermining the AEC in any way they possibly could. And that still goes on. It's inherited. Those people are all gone now. They're no longer there.
Yeah.
But some of that bitterness over the loss of that $80 million is probably what's carried this fight on.
Oh, yes. And it actually still permeates into that report of the National Academy, probably, and that insane recommendation that several thousand deaths are due to radon coming into basements, which is so ridiculous, I think. Well, that certainly adds a lot to the background of this whole thing. Well, fine. Well, any other points that you think worth mentioning here? We've covered a lot of ground here and a lot of background, a lot of valuable information.
I see there's a meeting going to be held shortly on the peer review system.
Oh, where is it? I hadn't heard about it.
I just saw something about it. And they're going to talk about who the peers are and how the reviewers, editors and the reviewers, how the editors get their reviewers and so forth.
Oh, yes.
And that's an important meeting, but I don't know whether the right people will attend.
I didn't... that somehow went by. I think there was a little squib in Science about it, and I didn't really read the article, and so of course one of the a lot of these peer review systems get to be old boy networks. They're repeated and repeated and repeated. The peer review system, perfectly logical thing. It's only the makeup and how it's administered.
There needs to be some way of stirring it up every once in a while. I don't know anything better, but it is in that shape, and I would say that the epidemiology business is the worst of the lot.
Yeah.
Only the ones who have an established name are allowed to publish anything.
And particularly anyone who tries to get in different points of view, they're just immediately. In fact, I have heard some awful stories, and since this is off the record, there have been definitely in some of the agencies, including DOE and even before that, ERDA, that somebody will want to make a study, of a certain thing, good scientists and so forth. Essentially, the message came through loud and clear. Well, fine, you make this study, but make sure the conclusions are this. They don't say it exactly in that way,
but that's clear enough.
It's with a raise of the eyebrow and a few other things. That message gets through loud and clear. So you get there's an awful lot of studies that come through in this particular.
I got told in a letter from a fellow, whom I actually asked to review my paper, he said, "Why would you take away the hope for these people?"
Yeah, this is the sort of thing. Well, but these are all the tough problems. But as I say, I always say, as long as there's all this money scaring people to death, we're going to have those incidents.
That's right. We sure are.
Well, thank you very much, John. I sure appreciate this, and you've really been a great deal of help and giving this very valuable background.
I hope you get something worth
well, fine. Well, this, I go back